Hi Math 215 students. In this second part of section 1.3, we're going to be talking about what we call linear combinations of vectors. Right, for this video, here are our outcomes. Before you move on from this video, please do your best to define the terms listed there and do the other objects listed there. We'll discuss these things as we go throughout the video. All right. Now, a couple of videos ago, we laid out a couple of big questions about linear systems. We said that when you have a system of linear equations, we wanted to know how do we solve one, and we talked about that in sections 1.1 and 1.2, and how we describe the complete solution set. We also talked about how many solutions a given specific linear system could have, and how we could figure out exactly how many solutions there were. And that had everything to do with whether the last column had a pivot position in it and whether or not there were free variables. All right, in this video we're going to start to address this last of those three big questions. We're going to talk about other perspectives from which we can understand linear systems and their solutions and the existence of solutions and so on. So let's get to it. I want to start by just pointing out a problem from your textbook. This problem is about two mines. So each day, on average, mine number 1 produces ore containing 15 metric tons of copper and 500 kilograms of silver. That's just what is in that mine. While mine number 2 produces ore containing 25 metric tons of copper and 450 kilograms of silver. So the problem instructs us to use vector v1 equal to 15, 500, and vector v2 equaling 25, 450 to represent the two mines' respective daily outputs. You'll see that in both vectors, the first coordinate contains how many metric tons of copper are produced on average in a day, and the second coordinate contains how many kilograms of silver that particular mine produces on average in a day. So the first question we want to ask is what physical interpretation can be given to the vector 3v1 plus 4v2? And the second question, if the company operates mine number 1 for x1 days and mine number 2 for x2 days, write a vector equation whose solution gives the number of days each mine should operate to produce 140 tons of copper and 2,800 kilograms of silver. And once you have that vector equation, can you solve it? Now, we haven't talked yet in this course about vector equations. We'll do that in this video, but we can talk about that first question. What interpretation can be given to the vector 3 times v1 plus 4 times v2? Now, as we talked about last time in the last video, 3v1 is the vector you would get by multiplying both the coordinates in v1 by 3. 4v2 is what you would get by multiplying both coordinates by 4, and then their sum just comes from adding together the corresponding entries. Now, if you think about that, 3v1, if v1 is the amount of copper and silver produced each day by mine 1, 3v1, it stands to reason, should be the amount of copper and silver produced over 3 days, right? If all you're doing is multiplying the coordinates by 3, that should give us about the amounts produced over 3 days. Similarly, 4v2, if we multiply both the coordinates by 4, that should give us roughly about the average production of copper and silver in mine 2 over 4 days. And so adding them together, we get the combined total output, measured in metric tons of copper and kilograms of silver, of mine number 1 over 3 days worth of production, and mine number 2 over 4 days worth of production. All right? Okay, now we are interested in dealing with quantities like this that are scalar multiples and sums of vectors. If you actually were to interpret 3v1 and 4v2, if you were to do the calculation out, you'll see that allowing mine 1 to run 3 days and mine 2 to run 4 days would produce 145 metric tons of copper and 3,300 kilograms of silver. Now, these kinds of quantities we can form by taking scalar multiples of vectors and adding them together are called linear combinations. So we'll say that a vector formed by doing that scaling and adding, the result is called a linear combination of the vectors v1, v2 up through vp, however many vectors there are. And we'll say that the weights are these coefficients, these numbers, these scalars we're multiplying by, are the weights in our linear combination. Okay, now in our exercise, we were dealing with the quantity 3v1 plus 4v2. We found out what that was. It was 145, 3300. And as you compare the left-hand side and the right-hand side, you'll see that the left-hand side looks like the left-hand side above. We do have weights or coefficients on our vectors, and we're adding them all up together, and we get a linear combination of v1 and v2. All right, now looking ahead just a little bit, we'll make a definition here. The span of v1 through v2, v through vp, this is the collection of all possible linear combinations. So as you can imagine, because these coefficients are free to choose, we can make infinitely many different choices for the weights on the vectors. And as we do that, we're going to produce infinitely many outputs, infinitely many different linear combinations. And the span is the set that contains just all of those infinitely many possible linear combinations of v1 through vp. Now we'll talk about the span a little bit later in the video, but let's take a look at another example of linear combinations. So I've got here the two vectors 0, 1, 2 and 0, 0, 3, and you'll see that in each of the equations below, I've assigned a different weight or a different coefficient to each of those two vectors. But when I do put those coefficients on those vectors and do the actual calculations, multiplying the constants through those vectors and adding the results, I'll get a bunch of different vectors out. 0, 1, 2 is a linear combination of those two vectors. Now you'll notice 0, 1, 2 was actually one of those vectors. We just took one of it and 0 of the other. So 0, 1, 2 is a linear combination of these two. So is 0, 0, 3 itself. The 0 vector will be a linear combination of these two. We can do that just by taking the weights or the coefficients to equal 0. And then if we get a little bit more crazy with our choices of coefficients, we can get vectors like 0, negative 2, 11, 0, 0, 0.7, 2.3, and 0, negative 8.79, negative 1.56. So now a question that seems kind of natural to ask is this. Given all the different variety of vectors possible to make from 0, 1, 2 and 0, 0, 3, you might choose a specific vector like 2, 7, negative 4. Could 2, 7, negative 4 be a linear combination of 0, 1, 2 and 0, 0, 3? Now, there are technical ways to answer this, of course, but as you compare these two vectors on the right with the result, you'll see that that first coordinate is going to give us trouble. No matter how we combine the two vectors together, the first coordinate is always going to be 0. And maybe as you take a look at the examples, you can see why that is. So you would never be able to choose coefficients on these two vectors to make the first coordinate be something other than 0. So the answer to this would be no. And we'll talk about how to answer questions like that more technically as we go along. All right, so now here is a key question for us that we're interested in, and here are three different ways of asking that same question. If we're given a vector B and a collection v1 through vp of vectors, all from Rn, our question we might start off asking, is B a linear combination of those vectors? Just like we did on the last screen, could 2, 7, negative 4 be a linear combination of the two vectors that followed it? Now, equivalently, you can ask the same question in this way. You can say, is B in the span of v1 through vp? Because remember that the span was the collection of all possible linear combinations. So asking if B is a linear combination and asking if B is in the span of those vectors is basically the same question. Next, if we think about what a linear combination is, we can also phrase this as, is there a solution to x1v1 plus x2v2 plus dot 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 plus xpvp equals b? Now, as you compare that to the first way of writing this question, you'll see that it's actually asking the same thing. What we have on the left is a linear combination. We're saying B, we're asking whether B can be written as a linear combination. Now, the question for us here is we don't know if the answer is yes or no, and so what we're going to do is put variables in the coefficient spots for the weights, x1, x2 through xp. If I can solve for scalars that will fit this equation, then the answer will be yes, B is a linear combination, and yes, B will be in the span. If I cannot solve for those coefficients, then the answer will be no. All right, so now let's take a quick look at this equation. This is what we call a vector equation. What you have is a bunch of vectors that are multiplying each onto an unknown scalar, an unknown coefficient. And what we want to know is are there values for those coefficients which will make this linear combination of v1 through vp equal to the vector b on the right-hand side. Now, what I've got here is a visual depiction. v1 I'm going to write as a column vector. v1, 1, v1, 2, these are just the first, second, all the way through the nth coordinates in that vector v1. I've got a similar picture for v2 all the way up through vp, and I'm multiplying each of those by the unknown scalar x1, x2 through xp. Now, we're going to try to make this look a little bit more familiar based on what we've seen so far in the course. And to do that, we're going to just recall what it means to multiply a vector by a scalar. We're going to multiply x1 through each coordinate of the first vector. We're going to multiply x2 through each coordinate of the second vector, and so on all the way through the end. And then if we remember what it means to add vectors together, remember I just want to add together the components in the corresponding places. And so if I do that on the left, I've got a whole bunch of them. I'll add that there. In the second entry, I'll add together all the second entries, and so on all the way through the pth row, or nth row rather. And then setting that equal to the vector b1 through b2, we actually get a system of equations. The first equation would read x1 v1 v1 x1 v11 plus x2 v21 plus dot 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 plus xp vp1 equals b1. The second equation would be this quantity here equal to b2, and so on. And that's a system of linear equations. We know how to solve those. Now, the way that we have solved systems of linear equations is by putting them into an augmented matrix and using row operations to reduce it. So if we look at what the augmented matrix would look like, it looks pretty similar to the expression above. Because x1, x2, and all the way through xp are our variables, we don't write them, we just write the coefficients on them, which would be the numbers coming from our vectors, as you can see. And then we would insert that last column, that last vector, as the entries in the last column of our augmented matrix. Now our question was, is there a way to choose the coefficients to make this work? Is there a solution to this vector equation? And the question that we would ask ourselves here, if we saw a problem like this, we would ask, does this augmented matrix correspond to a consistent system? Is there a choice for those variables that makes this work? Now, as we compare these two questions, we'll see that they've got the same answer. If we're able to find those coefficients x1, x2, and so on, we would have values to put into our equation. There would be a solution. On the other hand, if we were to row reduce this down to its reduced echelon form, and we found out there was no solution because there was a pivot position in that last column, then that would mean that there's no solution. The system would be inconsistent, and that would actually tell us that there's no solution to the vector equation either. All right, so here's a key fact. The solution set to that vector equation is the same as the solution set to the system having the augmented matrix formed by the columns coming from those vectors and the last column coming from the right-hand side there. The solutions to both of these are the same. And if there is no solution to one, then there's no solution to the other as well. So we have a couple different perspectives to start comparing things with. So far in the course, we've talked about systems of linear equations. We've asked whether there are solutions to the systems of linear equations, and we've talked about how to answer that using the augmented matrix, row reductions, and in particular looking for where the pivot positions are. Now we've introduced the idea of a linear combination of vectors and a vector equation, and we've just got done saying that the answer to the one question, is there a solution to a vector equation, corresponds very neatly to the answer to this other question, does the linear system have a solution as well? And we're going to be jumping back and forth from these perspectives throughout the course, so it's very important at this early stage that we spend some time kind of thinking about why these questions have the same answer and going through some of the ideas of this video. It will be very helpful to you as you go ahead. All right, so let's go back to that introductory problem again. We've answered the first question. We want to know if the company operates mine number 1 for x1 days and mine number 2 for x2 days. Write a vector equation whose solution gives the number of days each mine should operate if they want to produce 140 tons of copper and 2,800 kilograms of silver. And then once we've written the equation, our goal is to solve it. All right, so let's take those two vectors. Our desired output is 140 tons of copper and 2,800 kilograms of silver, and we just want to know how many days should we let each mine run. So if we'll let x1 be the number of days mine number 1 works, and x2 be the number of days that mine 2 works, then we can write an equation, x1 times v1 plus x2 times v2 equals our desired output. We should mention that the units that were asked in the problem do match up with the form that the vectors came in, so we don't need to worry about our units. Now here's our vector equation. We want to know, does it have a solution? Is there a certain number of days you can have mine 1 run and mine 2 run to get precisely this amount of the desired ores? In other words, taking a look at the way this is phrased, we could ask, is 140, 2,800 a linear combination of the vectors v1 and v2? Now, if we were to answer that, the easiest way is to go back to what we did for linear systems. What we'll do is set up a vector, we'll take this vector equation rather, and we'll make its columns the columns of an augmented matrix corresponding to a linear system for each of the coefficients x1 and x2. Now if we were to take that matrix and row reduce it, in reduced echelon form, I'm going to skip all the steps that went into this, but in reduced echelon form, this matrix reduces down to this matrix here, 1, 0, 28, 23rds, 0, 1, 1, 12, 23rds, and you can see numerically how much those right-hand numbers what they equal. So the bottom line is, what we should do, x1 should equal 28 over 23rds, or in other words, 1 and 5 23rds. If we let mine 1 run for 1 and 5 23rd days, and let mine 2 run for this number, which is equal to 4 and 20 23rds days, then we will get exactly a solution to this problem. We'll know how many days to let the mines run to produce the desired amount of ore. All right, now let's take a quick look back at our very first video or two. You'll remember that back then we were talking about building a diet, a menu of Cap'n Crunch and Yoplait yogurt, and we wanted to do so in such a way as to max out our recommended daily calories and our recommended grams of fat. When we did ask that question, we put these coefficients into an augmented matrix, and we talked about a solution to the linear system there. We could also have asked, though, is 2065 in the span of these two vectors 152 and 151? And there's a couple of reasons why you might want to do this. You'll remember that 150 and 2, these were the details specific to Cap'n Crunch, the number of calories per serving and the amount of fat per serving. And 150 and 1 were the details specific to Yoplait yogurt. And so by phrasing it in terms of vectors, we can sort of collect each food's information in a single vector, which is kind of a nice way to think about it. All right, now if we were to solve this, we would, again, just put 2065 as the right-hand column, and we put our two vectors in there. And whether we're solving the system or asking, is this in the span, our answer will come from row reducing the matrix. We do get a solution. We would let x1 be 155 over 3 and x2 be negative 115 over 3. So the answer is that yes, 2065 is in the span of these two vectors. Yes, there is technically a solution to this, but as we pointed out in the earlier videos, it's not so practical to have a negative number in our answer. How do we get rid of a certain amount of Yoplait yogurt? Well, moving on from that pleasant thought. All right, so now as we move on, we'll remind you that the span of V1 through VP is the collection of all possible linear combinations of V1 through VP. And remember, there are usually going to be infinitely many different ways of putting coefficients on these vectors, and a linear combination is anything you can get out. So there will usually be infinitely many different vectors in the span. So let's end this video by talking about pictorially what spans of vectors can look like. Now if we take a look at a specific vector v, we talked in the last video that if we were to take all the scalar multiples of v, we would get a line passing through the origin and v. And if we take all the possible scalar multiples of v, and v is the only vector in our set, that is the set of all linear combinations. So the set of all linear combinations from a single vector, possible from a single vector, forms a line through the origin and v. Now if I have a set of two vectors from R2, the span of uv could end up still being a line through the origin if u and v were either pointed in the same direction or exactly opposite. Or in other words, if u and v were multiples of each other, then putting them together, scaling each of those and adding them together, will still only give you something on that line through the origin and each of the vectors. On the other hand, if u and v are not multiples of each other, then the span of u and v actually ends up including every point in R2. And to see that, let's take a quick look at what we've got here. I have drawn the vector v, which is 3, 2, and the span of v is all of the points on this line. The vector u, I'm taking to be the vector 1, negative 1, and the span of all of its points is on this line. But let's remember that with linear combinations, I'm allowed to scale either u or v and to add the two vectors together. If I were to take one u and one v and add those together, our parallelogram rule tells us that we would end up with the vector 4, negative 1. Now if I were to take 2u and 1v, add those together, that would give me the vector 5, 0. Now if I were to take some random vector like 0, 3, now it's not at the intersection of some of these green lines and green and red lines, so it's not going to be a perfect multiple of u and a perfect multiple of v. But as I take a look at, is it possible to get from the origin to the point 0, 3 by either walking forward or backwards in the direction of v and forward and backwards along the direction of u? Now I'm allowed to use both directions, remember. And I think you'll see that the answer should be yes. If I were to travel along v about this far, so maybe 2/3 of v, and then if I were to walk backwards in the direction of the green arrow, I could hit the point 0, 3. So there is an amount of v and a negative amount of u that I can add together to get the point I desired. And the same thing is true for any point in R2. If I'm allowed to take steps either forward or backward in the red direction, and to take steps forward or backward in the green direction, hopefully you can convince yourself that by taking, fractional amounts, maybe taking smaller steps or larger steps, you can travel to anywhere in the plane walking along those two directions. All right, now similar things happen in R3. If our vectors have three components, there are a few differences, but the important thing is the shape of things. If you have a vector from R3 that is not equal to the zero vector, then the set of all linear combinations of that vector just ends up producing a line, the same as it did in R2. The span of a single vector that's not zero is a line. And similarly to R2, the span of UV is either a line or a plane. Now, to talk about that second option, let's take a look at a quick example. Let's suppose I wanted to take a look at the span of 110 and the span of 201. What I've done in the picture below is just generated a bunch of points by choosing different coefficients for the linear combination. And I end up with a bunch of points that sort of seem to fall in a certain direction. Now I've drawn this in GeoGebra, and you can kind of see, it's a little cut off here, but we've got these points in that span, and they all seem to lie on a certain plane. Now you should ignore the little dark green dots there and the red dots. They form the axes, the x and y axes, but plane actually is pointing in such a way that the vectors I chose are both part of the plane. The other plane you see there, the gray plane, is the xy plane. So, in general, if you have two vectors, neither of which is a multiple of another, then their span will sweep out a plane. All right, now, one thing we haven't talked about is what would the span be of three vectors chosen from R3? Now, to answer this question, maybe you want to take a stab at it before we go through it. Feel free to pause the video. But if we have three vectors in R3, if those three vectors were all pointing in the same direction or in opposite directions, if the three vectors were all multiples of each other, then the span would still be a single line. If we ended up having two vectors, u and v, that were not multiples of each other, but then the third vector, w, was a multiple of either of those, then you can see that basically our span just is what we get from those two vectors, and we would get a plane as well. On the other hand, it is possible for the span of three vectors in R3 to equal all of R3. If you can imagine that your vector u points straight in front of you, so steps in the direction of vector u are going to take you either straight forward or straight backwards, while vector v is the vector lying exactly to your right, so steps in the direction of vector v will take you either to the right or to the left if you walk backwards. And let's imagine now that you had some magic shoes that allow you to take steps into the air, steps vertically. So w is pointing straight up, and you can either travel upwards or downwards, taking steps in that direction. Hopefully you can see that if you had that capability of taking steps in each of those directions, you would be able to travel anywhere in R3. And so the span of three vectors in R3 can be R3 if the vectors are not pointed in the same direction as each other. All right, now we've talked about one of the big questions from before. What are other perspectives from which we can understand the problem and solution? And in this video, we've talked about linear combinations and vector equations, and we've talked about their connections to the concepts of existence of linear solutions and to what we see in an augmented matrix. Just one more plug, please spend some time going through the connections between these, and it will benefit you in the future. We're going to be talking in future videos about still other perspectives from which we can understand linear systems and vector equations and all of the above. And so before you leave this video, please take a second to look at this list of outcomes. Make sure you can do each of these things, and let me know if you have any questions. See you in the next video.